I'm going to be talking about a bit of a journey of the Shopify infrastructure. This is the kind of talk that I would love to have seen from companies like Twitter, Facebook, or some of the other companies about how their infrastructure got to where they are today. And Google has some of these talks where they talk about what Google looked like in 2001 and what it looks like. Well, today it's so complicated that I think they barely understand how it all fits together. But it was really interesting to see how their infrastructure evolved. So what I want to talk about is, as Rachel said, the past sort of 10 years of a very specific history of one platform and how we got to the scale that we're at today. So I work at a company called Shopify, and what we do is we help people sell things, whether you're selling them online or you're selling them on your phone or wherever. And in the past 10 years, we've grown a fair amount. And I want you to keep these numbers in the back of your head while I give this talk, because it's quite applicable for everything that happens. We do tens of thousands of requests per second. We can do a massive amount of checkouts. We've served a lot of transactions, a lot of money. Downtime is very costly for us and our merchants. And in the past couple of years, we've also grown tremendously in terms of the number of shops that we serve. And we have one particular problem that sort of dictates everything that we do on the infrastructure team at Shopify, which is what we call sort of the flash sale problem. We have these merchants who can drive a completely disproportional amount of traffic to us. And this creates massive problems for us. It's things like from 1 second to the other, there might be a 2x, 3x difference in the amount of traffic that we have because there's some launch of this guy's shoes, or we have Super Bowl ads that drive a massive amount of traffic. And if you've ever tried to visit one of the websites during the Super Bowl, and for all the Europeans, it's a big North American event that doesn't matter that much to us. If you try to go to some of these websites during the Super Bowl, they often have problems. And we have tons of merchants that go on the Super Bowl every year at this point. Not tons, but 1, 2, 3. I think 3 last time. And then, like every good story, and this is the story of our infrastructure, there's a villain. And currently, our villain is Kylie Jenner. She's an American celebrity sprung out of the Kardashian family, which is famous for being famous. And she sells lipstick. And when people can't access this lipstick, they get fairly mad. And this is a big problem for us. It hurts our merchants' trust because with Shopify, it's sort of a white label experience. Their customers has no idea that it's Shopify's fault that they're down due to their scale, and not Kylie's fault. So she gets all of that, and then she gets mad at us, and we try to fix it. I think there's even episodes of the Kardashian reality show where Shopify is down and they're filming. It's a mess. You can find it later, I'm sure. So really, we're dealing with these problems of scale. We've grown a lot in the past 10 years, and I want to tell sort of this story of the evolution of the Shopify infrastructure and what we've tackled and how we're getting to the point that in the next 2 months, we're going to be running out of multiple data centers. But 10 years ago, we weren't even thinking about that stuff. So the way I think about Shopify is sort of on this spectrum from a single-tenant platform to a multi-tenant platform. It's cut off a little bit here. And when Shopify started, or on both sides of the spectrum, there are sort of benefits. If you're a single-tenant platform, it means that you're running just one shop. There's one database per shop. On a multi-tenant platform, in the most naive implementation, you have one database for all of your shops. And both of these approaches have sort of their own benefits, right? Okay, so I'll have to be the guiding hand here a little bit on the sides here. So we have single tenant on one side, multi-tenant on one side. And this is sort of a spectrum. If you have a completely single tenant solution with one database, then you have some advantages. And if you have a multi-tenant solution where everyone runs on one database, you have some other advantages. So there's really a bunch of spectrums hidden in this. If you have a multi-tenant platform, there we go. If you have a multi-tenant platform, you have a large amount of capacity. You have a massive database, so if one shop has a big sale, they can sort of steal a bit of capacity from the other ones. And then later, when another shop has a big sale, they can take some from some of the other shops. But if you have a complete single-tenant platform, that becomes quite expensive because you need to provision a database for each one. This has sort of the secondary benefit of having good utilization. If you have a big multi-tenant solution with many stores running on one database, then you can utilize that database and the hardware that you have better by sharing resources between the shops. Whereas in the other solution of having just one store per sort of set of hardware, you don't have that. And this sort of gives us a platform that is good for flash sales and multi-tenant, and the single tenant is not quite as good for flash sales because you have this problem of a single store taking a massive amount of traffic will be very costly per shop. And there are some companies out there that are really good for doing stuff like that, the single tenant solution. Then there's things like the multi-tenant solution is just kind of cheaper. You sort of leverage the network effect of having all these shops to sort of take costs from each other. And on the single-tenant side, it's expensive. You have to care about hardware for every single shop. We have 300,000 shops, 300,000 databases. That's way too many to manage. Then there are some benefits on single-tenant, like you have complete isolation. If Kanye's shop completely breaks, it doesn't break anyone else's shop. Whereas in the multi-tenant, this sort of naive multi-tenant solution, you have that problem. Scalability is also great for single tenant because you can just make that one database bigger if that shop grows big enough. And so some of these don't even have sort of a green end. These are the extremes of a spectrum, and in the middle of this spectrum, we have some kind of middle ground that tries to harvest the best of both worlds. And this is sort of what I've been exploring for the past 3 years of how do we get the best of a single-tenant platform and the best of a multi-tenant platform in one platform. I refuse to accept that we just have to be multi-tenant and just take all of these things and then give up all the things on the left. I want to get the best. I want the entirety to be green. So over this talk, we'll talk about how to achieve that. So if we go back to the spectrum, in 2004, our founders created this snowboard store, and that was the first Shopify store. They created a platform to sell snowboards, and it looks something like this. Classic, like, mid-2000 web design. And so we launched that, but they realized that their business wasn't really in selling snowboards. In 2004, e-commerce was kind of finally reviving after the dot-com bubble, and there was a severe lack for good, customizable e-commerce software out there. So they sort of pivoted, and 2 years later, they created a multi-tenant platform to support many snowboard stores, many stores in general that could, and then Shopify became a multi-tenant platform. Instead of this Ruby on Rails app hosting just the one store, it could now host, well, as many as it could until the database broke. So where is that golden middle? Where do we get the best of the single-tenant world of just running that one snowboard store that can never impact any other store, and then having that big platform that supports all of them? So from 2006 to 2012, we moved a little bit in on that spectrum. We started doing a lot of work here and there to optimize the application to get a little bit more of the benefits of the single-tenant side and a little bit fewer of the drawbacks of the multi-tenant side. So for the first 6 years of Shopify's history, we did sort of what most companies did. We focused on our product, and every couple of months, someone would go and optimize the performance. There's a lot of low-hanging fruit. If you did a profile on an application, you might be able to get 5–10% of your CPU time back for some dumb N+1 somewhere, or spending a lot of time just doing operations that you don't need to do. You can do a lot of vertical scaling, meaning you can just increase the size of your database cluster, increase the number of workers that you have, and all these kinds of simple things. You can do a lot of caching. Our application is very cache-heavy because we have a lot of sort of just traffic onto stores that don't do write operations. So we did a lot of this sort of stuff for the first 6 years. But then, at some point, you reach a limit. And we reached that ceiling in 2012, and there's a legendary picture of our CTO passed out, face-planted on the floor after having worked for months to try and support one of the biggest stores at the time. And we reached a point where we couldn't vertically scale anymore, because at the end of the day, you can't cache a write. You have to scale your writes at some point horizontally. So in 2013, we started working on database sharding. And this is when a full-time infrastructure team was created at Shopify, because we had to start working on database sharding and scaling horizontally. And only the MySQL side was sharded. So before, our infrastructure looked something like this. We had some load balancers, some workers that did some work, a database, some Redises, some Memcache, and this all sort of worked together. And then in 2013, we split the database into multiple shards so that the write traffic could go out. And the reason why we have this write traffic is that if you're trying to sell something and you're trying to sell a lot of it, we need to create checkouts, we need to create orders, we need to take payments. There's a lot of writes that have to go on, and it have to be quite consistent, and that's one of our big challenges. So we did this in 2013, and really all of the deadlines of our team is around Black Friday and Cyber Monday, which is a big American holiday where Americans shop more than usual. So we did that, and it worked really well for a long time. And until then, sort of the write capacity or the scale capacity of Shopify had been the biggest threat to our existence. We were terrified of these customers taking us down, and on the other hand, we didn't want to say no to customers who were driving a lot of traffic. We could have just said, we're not going to be a platform where you can do this kind of thing, but instead, we acted in a way where we decided we want to be the only platform in the world that can support these kinds of sales. So in 2014, the biggest threat to our existence was that we had this pretty big app at this point. We were in the hundreds of servers in our data centers. We had tens of data stores and all this kind of stuff. And many of these sort of became single points of failure. And it may sound somewhat embarrassing that just 2 years ago we had single points of failure in our infrastructure, but it just hadn't been a priority to us because the threat of all these celebrities selling was much, much higher than that of a single database blowing up. So in 2014, we started working on resiliency. And the way I like to think about resiliency is kind of like in chemistry, if you have a big surface area, you're going to have more reactions. And it's sort of the same with errors. If you have a lot of servers, then there's just inevitably going to be more errors happening. If you have one server, the probability of you running into a kernel bug in a year is pretty low. If you have 1,000 servers, the probability of you running into a kernel bug in a year is pretty high. If you're Facebook, if you're Google, and you have servers in the millions, you're running into kernel bugs all the time, and they have kernel teams to solve this. So as you get larger, more errors will happen, and you have to deal with it. This is really when you have to transition from this sort of pet mentality of your servers and your infrastructure to the cattle mentality. So errors are proportional to the surface area of your platform, and we started reaching that critical mass in 2013, 2014, where outages of these small components would sort of disproportionately propagate into the rest of the platform and cause these cascading failures. So we started operating with this mental model of a resiliency pyramid, where we had to think about certain errors that were happening in our platform and start getting them to not propagate downwards. So we were really at the very bottom here. We didn't have any idea what happened if one of our database nodes really blew up. It hadn't been a threat to us at that point. So we started working on things like mapping out all the single points of failure, making sure that if the caches were down and we hit a store, that it would be fine, that if we had warm caches and we hit a store and the database was down, that it would be fine, wrote test cases for all of this stuff, and then started fixing them. And we wrote tools to do these things. We wrote a little proxy that sits between you and all your data stores in development that allows you to easily emulate error conditions in development. So you can do like, hey, for this test, take down this database and see that everything happens. And so we sort of mapped out the entire application, all the single points of failure, and did this in 2014. So in 13, we optimized the database. In 14, we did a lot of resiliency efforts. And in 15, we started working on multiple data centers. So at that point, we'd only really run out of one data center. The risk of that one data center going completely out and being able to fail over to another data center was just not as high than all of these other things. Worst case, we would have to just provision a new data center. We would have to be down for a couple of days, but it wasn't the biggest risk at the time. But in 2015, that became the highest priority, and we started setting up a second data center. And what this boils down to is that you have one data center that runs all of the different shards and so on, all of Shopify, and then you have another data center, and you set up replication from the one data center to the other data center, and then you somehow sort of move all of the traffic. So what we did was we did a lot of work to go from the one data center to the two data centers, and then we built this script that can run the entire failover process in just about a minute of downtime on Shopify. So sometimes if you see a maintenance window on Shopify for going down for a database failover, it's me running this script to fail over the entire data center in about a minute. And so it has a couple of steps here. It updates sort of a service discovery layer and says, OK, the data center is now going to move. And then it takes the checkout down. So if you're going through a checkout while we're moving data centers, it will show you an error. Hey, please come back later. If you go to a store during the time, because the store is read-only, that's completely fine. So most stores don't even appear to be down unless you try to perform a write. And then we sort of stop everything in the one data center, make sure that the replication is caught up in the other data center, then start everything back up. We tune our load balancers, so all the traffic that went into the old data center now is proxied over to the new data center, while we sort of update our internet routes to announce the IPs out of the new data center, and then everything is moved. And this takes very, very little downtime. And then you end up in this situation where data center 2 is now the primary and is replicating in the other direction, and then we could always fail back. And we've done this exercise probably around 10 times or so. The very first time we did it, we were all sitting in a room. There's about 20 different people looking at 20 different dashboards, and it was kind of like what I imagined, if after a space mission, they all hug each other afterwards, and that's what we were doing, and people were on Hangouts, and it was a big thing. And now it's like two or three people running this script, and it's still a little bit of a bigger deal than I want it to be, but it's pretty small thing to fail over a company our size at this point. So that's really great. So we got really good at this multi-DC thing. And then in 2016, we've been working on this concept called pods. And the idea of pods is really, let's take all this stuff that we learned from 2006 to 2012 about running a really, really good application and optimizing it and performance increases. Let's take that. Let's take all of this stuff that we learned about database sharding in 2013 and all the stuff that we've learned since that. Let's take that as well. All this stuff we learned about resiliency in 2004 and all this stuff we learned about multi-DC in 2015 and sort of see if we can marry all these concepts in a way that makes sense and do something with that. So what we came up with was this idea of a pod. And the idea of a pod is to take this sharding idea further. So a shard by itself, in sort of Shopify terminology, is just sharding the database. We didn't shard everything else, only the database, because that was the most critical thing at the time. So what a pod is taking that concept to the extreme. We take the workers, we isolate them for a group of shops. We take Redis, and we isolate it for a group of shops. So basically, it becomes like running multiple deployments of Shopify at a smaller size. So the goal is that if we have these completely isolated units of Shopify, then we can run those in multiple data centers. One can run in Asia, one can run in Europe, one can run in India, one can run in North America. It doesn't matter. One shop does not need to talk to another shop. There are some exceptions to that. Things like if you're talking to the API, you don't want to have to care about shards or any of that. Or if you're a partner and you have shops in Asia and you have shops in North America, you don't want to care about that. So there's all kinds of sort of global challenges to this. So we had this. 2013 had led us with this architecture here when we did the database sharding, and what we wanted to move towards was something more like this, where we have these self-contained pods, self-contained deployments of Shopify. And instead of managing one big Shopify, we manage a lot of small Shopifys. And then if we have that, then it doesn't matter where these things run. Some of them can run in data center 1 in North America, and some of them can run in data center 2 in Europe. And then all the European customers could be on data center 2 in Europe, and all the North American ones could be on the ones in North America, and we could have multiple data centers there, replicate them, fail over the pods independently, and we just have this really nice infrastructure. And then if we return back to that spectrum chart from before, we've arrived at something really nice. We haven't quite reached the middle yet, but we've gotten a lot better. So in the capacity, on the capacity spectrum, we have much better capacity than before. A naive multi-tenant solution doesn't lend itself very well to running in multiple data centers, but now we can do that. If we wanted to spit up Google Cloud pods of Shopify, we can do that. If we wanted to go into Amazon, if we want to start experimenting with the cloud, we can do all of that stuff. Utilization is a lot better. Flash sales is also better because of the more capacity. It's even cheaper because now we can start sort of having vendors and data centers bet against each other. Isolation is better because now you have groups of shops, so if one shop blows up, the blast radius is sort of limited to that pod and not the entirety of Shopify. And the scalability is also better because we can now run out of multiple data centers and scale sort of independently. And so we're not quite there yet. Everything is not green, but it looks a lot better. And flash sales was one of these prerequisites that I set up before. It sort of is what everything comes back to on the infrastructure team at Shopify. And what we do with flash sales is that we're limited by the CPU on the workers. The databases are all over-provisioned and not the bottleneck for us. Instead, it's the workers. It's the Ruby on Rails workers that serve the application. And so what we have is we've written, on top of some of our resiliency primitives, we've written it so that workers can sort of be shared between pods. So if one pod is experiencing a massive sale, it can take some workers from some of the less busy ones and then serve the traffic and then give them back to the other pods. And this works really, really well, and we sort of get the best of both worlds. So let's see what that looks like. If we get a request in this setup, you are going to do a request here where you get to these beautiful shoes on myshop.com, and myshop.com resolves to one of our IPs. Our IPs are announced out of multiple data centers, and you go to the closest data center and enter our networks. And when you enter our network, you reach this software very dearly called Sorting Hat. And what Sorting Hat does is it looks at the request, and based on the request, it thinks a little bit and decides which pod this request is destined for, and then routes it to the appropriate data center. So your request goes to one data center, enter our network. The load balancer's Sorting Hat module looks at the request, decides, is this request is for pod 2? Okay, is pod 2 local to this data center and active in this data center? If yes, then you just send it to this data center. If not, you proxy it somewhere else. So if you're going to Amsterdam, you might be proxied to, say, Virginia to be served your request. And then you enter another Sorting Hat in that data center. It knows that it's local, and it's all fine. So this is sort of the multi-DC strategy in a nutshell. And I just want to give a shout out here to OpenResty. So this Sorting Hat module is written as an Nginx module, and we use Lua for this. And this is some of the best software, that we run, in my opinion. Nginx is extremely stable. We've found very few bugs in it, despite our surface area on this. And with OpenResty, you can extend it with Lua. You can do crazy things like customize the load balancer. So we implemented an exponential weighted moving average for our load balancing. You can do things like serve SSL certs that are different. In our case, all of our customers point to the Shopify IP, but based on the host name, we can serve them the appropriate cert dynamically out of a database with this. You can do anything that you imagine at a database layer. If you're running Docker containers, you can get all the containers from a service discovery layer. What this stuff can do is incredible. And what we use it for with Sorting Hat is that we go into the request and look at it, and then we route it appropriately based on what the request looks like. That's the Sorting Hat module. So if we have this architecture, we need to set up some rules of what Shopify can do to run in this setup. And the two rules are, rule number one is that any request that comes into Sorting Hat needs to be annotated with wherever it's going. So Sorting Hat needs to make a decision of where this request belongs to. What shop does it belong to? What pod does it belong to? If you're going to a data center in Chicago and the Sorting Hat in Chicago can't figure out what shop this request belongs to, it just has to forward for you. It doesn't know whether it needs to send that request to Amsterdam or to Asia. It has no idea, so it's just going to error. So every single request needs to honor that rule. Rule number two is that any request can only touch one pod. If it touches multiple pods, multiple Shopifys, it means that you might do a request to Amsterdam that also needs to reach to Asia and North America and everything in the same request, and that's a mess. That has really bad consequences in terms of resiliency, that these requests now rely on multiple deployments of Shopify. So these requests could look something like this. You get a webhook from, say, Stripe from a payment, and then instead of having the shop domain, in this case, you would figure out which shop this request is going to by looking at the URI. So you have to teach the load balancer about these different things. The other problematic request might look something like this, where in the past, we might have gone over every single shop and tried to count all of them, or we might have had some operation to try and upgrade all the themes around all the Shopify stores on all the different deployments of Shopify, all the pods, and these we can't have any longer. So in the first case, we need to teach the load balancer how to route that URL, and in this case, we need to teach Shopify to not reach to multiple shards in the same request. And so we came up with this thing called shitlist-driven development. Because to honor these two rules, we had 500, if not 1,000 different code paths that violated these rules. Our infrastructure for 12 years had relied on the very underlying assumption that you could do these two things. You didn't have to care. Shopify could just figure it out at runtime when the request came in. So with this overwhelming list, we came up with primitives to sort of create a deprecation API. And usually with deprecation, what happens is that if you use the new API, something will yell at you, but you can still use it if you want to. What we did with shitlist-driven development is that instead of just deprecating and spitting out an error message, we whitelist all the existing usage of that API, and you have a big checklist of everything that needs to get fixed. And then, if you violate that, you raise an exception. So it looks something like this. If the shitlist includes your class or your request, then just do it. Otherwise, print out a friendly message and come talk to us, and we'll figure out how to do it together. But the point is that we sort of stop the bleeding to violate these multi-DC rules and then go fix them. And then we're left with this massive checklist of everything we need to fix, but there is sort of a feedback loop. We kill them one at a time. And this refactor is coming up on taking a year for us to do. So it's really, really helpful to have that very tangible success metric. So for our routes, the shit list might look something like this. The shit list is your routes file. So here are all of your different routes. In Shopify, we probably have 500 of these, but these are just a subset of the one that you can see are a bit problematic. Things like sign up. That doesn't really inherently belong to one Shopify. So you have to sort of go to every single pod and ask it like, hey, do you want to sign up this store? It's European and fresh and whatever. And then all the pods respond back like, I'll take it, and load balancer picks a random one. Things like changing your password or recovering your password, you actually have to ask every single pod because we don't want to leave that abstraction to the developer or to the merchant about what pod they belong to. So all of these are sort of shit listed because we don't know how to route these. So we added this syntax on top of the Rails default route syntax to have a routing method. So in the first case, we know to extract the shop from the param. And in the second case, we know to use this special sign-up method. And in the third case, we need to try all the different pods and aggregate the results somehow. And in this last case, if you just visit a store, you can extract the shop and therefore know the data center from the host from the host parameter in the HTTP config. And so somehow we needed to teach the load balancer about all these Rails routes. So what we did was we parsed this entire AST that the Rails routes generate and made it into JSON that our sorting hat Lua module could read. So it looks something like this. The Rails routes are serialized into JSON, and the JSON is then read and interpreted by sorting hat. Sorting hat being this module that sees request and routes it to the appropriate data center. So this JSON might look something like this. It basically just has like 5,000 or like 500 or 1,000 different routes that just match regexes. It knows the routing method, so it knows when it sees a request that matches this regex for the URI, then it figures out what the shop or pod that request is going to from the method defined here. And the vast majority of them are shop from host, but there's a ton of others that don't go through that. So if we then reiterate this diagram, what happens is that you get that request to sorting hat. Sorting hat looks at this giant JSON file that is generated from the routes from the web app, and then it knows, based on that request, which pod in the world that it belongs to. And then, if you, on top of that, honor these two rules of every request of sorting hat being able to know where every request goes, and every request only touches one pod, you have the isolation to be able to run in multiple data centers. And I think it's really neat how all of the different efforts from over the years sort of play together. The resiliency that we get through isolation is quite well, but we also get isolation through resiliency. We get scalability through all of these different things, and the multi-DC that we've achieved really comes through the isolating of Shopify into many, many small Shopifys that can run independently. And so just a couple of thoughts on the future, because we haven't quite reached that middle yet. From the spectrum before, not everything was green in the middle. So we're pushing the boundary further and further towards the center, but we're not quite there yet. Maybe 2017 is when we'll reach it. And two of the things I would like to work on in 2017 are things like doing 0 downtime pod failovers. When I fail over a pod from one data center to the other, I don't want any customer impact whatsoever. So what we're thinking about doing is that when we fail over the data center or a pod from one data center to the other, we tell the load balancers in the origin data center to pause all of the requests. Then we move everything, and then we resume and let the requests flow through. This means that there is not really any disruption for customers. If you're doing a checkout while we do a pod failover, it will just be slow, but it will still succeed, and nothing will be dropped. Something else I would like to do is isolating the shops further. We still have the blast radius of one store blowing up. We'll sort of propagate into a pod. I would like to put more constraints on single shops so that doesn't happen as much by looking at past disruptions. But that's really what we've been looking for 2017. In just about 1 or 2 months, my team will hopefully launch Shopify in multiple data centers with this pods approach in time for Black Friday, Cyber Monday. If we don't, well, fuck. Thank you so much.
So the first question is, how do you handle transactions in the sharded SQL?
Okay, so I think what's implied by that question is, how do we handle transactions between the multiple shards in this setup? That's how I'm going to interpret the question. We have this nice property in Shopify of one shop not caring about another shop. So the transactions are really isolated. If you're doing a transaction on your shop in updating an inventory count or products or things like that, you're not going to reach across the other shards because you can't do transactions that span multiple shards. It just doesn't work. There are multiple databases. They have multiple sessions. There is one database that I didn't talk about because it's sort of a very lengthy talk on its own, and it's what I've spent the past 4 months on, is that we have another database that is sort of the master database. It hosts things that don't belong directly to a shop, things like billing, things like partners, things like API, all these things that don't inherently belong to one shop. And you can't do transactions between a shard and that either, so we just kind of like do best effort and put all of the transactional things back in the shop and then backfill them into the master. So basically, the answer is try to avoid doing cross-shard transactions everywhere you can. If you can't, you need to try to refactor your code or just live with the drawbacks of not having transactions cross-data store.
Yeah, transactions hard.
Yes. Yeah, don't do sharding if you can avoid it. Don't do it.
Okay, the next one. Did you extract microservices for your app, and did that help with the scaling?
Yes, so this is something we debate a lot internally as well. So without going on a too lengthy rant here, I think microservices in many companies is sort of overcompensation. I think good object-oriented programming can get you out of most of these things. And I don't think you need to enforce this TCP/IP boundary to have good software. That said, there are some boundaries when your application sort of obviously just belongs in different apps. The example of Shopify is this: we have these sharded tables where a shop has all of its data, but we also have like the API and partners and billing and stuff like that belong to sort of a global database. So we want to actually extract these things into services because they don't belong to a single shop, and Shopify should only care about shops. So billing should live in its own thing, partners should live in its own thing, and API should live in its own thing because these three things don't belong to multiple shops. And with API, I don't mean the actual API of retrieving your products or performing a checkout, because that still belongs to a store. I mean things like authentication or creating apps and things like that.
Okay. One more. How do you handle the pod deployment?
So the way we handle deployments right now is that we just deploy all the pods at once. In the future, I would like to do canary deploys or ring deploys, where we deploy to one pod at a time. Right now, we just deploy to all of them at once, and that works fine. But something I would like to do over the next year or two is to try and deploy to one pod at a time, because it just minimizes risk when we have all of our developers able to deploy all day.
All right. The last question is, are you using Kubernetes?
I don't think that's public yet.
Okay. All right. Well, one more round of applause for Simon. Thank you so much.